Guys, what are vector support machines?
So guys, we're going to be talking about vector support machines in this lecture. Vector support machines. Okay, so I'm quite excited about this lecture because we have a lot of stuff to cover, a lot of details to actually go through. So to get started, first I'm going to be considering a graph. I'm going to create just two vectors. One is w bar and one is u bar in two different directions. And we're going to have one line which actually flows through them. We're going to have another line over here which is parallel to that line. And we're going to have 2 points here. We're going to have the center of that be labeled like that. So what I want to do is I want to construct w bar dot product of u bar is greater than or equal to c. Here, I also want to consider w bar dot u bar plus b, a constant or a variable in this case, greater than or equal to 0. So then the decision rule applies. So what is the decision rule? Let's talk about that. So c is equal to minus b. Why? Just keep that over there. What would you get? What is this? Compare this with this. C is equal to minus b. That's how we got that. So what also we can consider is w bar dot product of x. In this case, I'm going to consider x plus, and I'm going to say plus b greater than or equal to 1 in this case, for example. Then what would this be? We're going to have another one, w dot x bar minus, so I'm going to say plus b less than or equal to minus 1. So two different equations here. So we're also going to consider y of I such that y of I is actually plus 1 for positive samples, and we have minus 1 for negative samples in this case. So let's see how we incorporate this into this equation. What would we get? You would be multiplying y of I, so w bar dot x bar plus b greater than or equal to 1, or what's the other opposite? We have or less than or equal to minus 1. So that would be for the final result. Let's consider y bar x bar dot w bar. We can say this is plus b minus 1 greater than or equal to 0. So this is the first equation. We can have, in this case, we would have this answer, x bar dot w bar plus b. We can say since it's minus 1, we converted this side, so that will be a plus 1. We can say that less than or equal to 0. So we got our two equations here. Let's mark them equation 1 and equation 2. Let me just circle them in a box so we can actually identify them easier. Okay, great. So now let's actually go and incorporate what we learned. So let's consider a graph here. Let's say we have two different possibilities. Let's say we got minus, minus, and we got a plus, plus here. And we have two parallel lines right over there. Perfect. So let's see how they actually connect. So I'm going to say there's vector, it passes to minus, and one passes to plus. And I'm going to call this x plus, and I'm going to call this x minus. Okay. So what we can do here is we can actually go and combine this. So we can say we can create a new vector of this. So this would be x plus minus x minus. So that's what we would actually get. So now let's continue calculating the width. So the width would be here, this one is equation, x minus, x minus. So what would that be equal to? So we also have to consider the dot product. So we're going to consider the dot product of the magnitude to get the scalar vector. Then what is this value here? So from 1 and 2, we can say that this value is 1 plus b, this value is, sorry, this is 1 minus b, and this is 1 plus b. So this is a plus. So how do we actually go to that? Oops, I'm sorry, forgive me. Yeah, so how do we actually go to that? What would we get? We would get, so what would we be getting? We're going to actually get, if we substitute these two values, we're going to get minus 2b by into w bar by w. But since we're only considering the maximum and we're only considering the magnitude, we're going to neglect the negative values and the constant b. So we're going to get 2 by w bar, magnitude of w. And this will be considered as the max in this case. So what would that actually lead to? So this would be the max. We're going to drop the constant of 2. So we're going to get 1 by w as a max. And for the min, what we're going to be considering is the basic minimum function. So that's half of w bar whole square. So that's our min. So we're going to be considering language's function here. So let's do it by L. So we're going to consider the minimum, that's half of w bar square. And we're going to consider the constraint. So we have alpha 1 as being alpha I being the main case. Then when you use equation number 1, from 1 we have y of I, w bar dot x bar plus b minus 1. So in this case, now let's do a partial differentiation about that. Okay, let's use a partial differentiation of w bar. So this would be 2 by 2, that would be w bar. I'm just doing this step by step for you guys to see. This would be y of I, w bar, x bar, plus y of I, b. Then we have minus 1 in this case. So if we go consider that further, that would be w bar, this would cancel. And with this partial differentiation, we would get minus of alpha I, then we would get, this would be 0, and this would be 0. Then we would get basically alpha I, y bar dot x bar. This would be 1. So that's what we actually get in this case. And this would be equal to 0, since the partial differentiation is equal to 0. So what we would get, final answer, w bar xi, yi. This is the final answer which we're going to get. But in this case, since we have this, we're also going to do a partial derivation of b. So what would we get? We would get minus alpha y, which is equal to 0. That implies is equal to 0. So that's the final answer. That's how we do it, guys. That's how we actually solve this issue. So let's continue. So we have, one second. Okay. We have L is equal to half of. Then we got y, x bar. The same thing again. J. Okay, and then we're going to actually minus this. We're substituting the values actually in the above equation which we got. So we have y of I into j, yj, xj. Nothing much of a difference. Next, we also forgot we have to substitute this value as well. B, and then we're just going to add alpha. So this would give us, by actually cancelling out this value, this b will go over here, and to get an approximation of this will come into the front. And let's see, we have half of this, so we're just going to actually biplot this into a double squared path. So what we're going to do is we're going to say minus half of, let's see, I, j, x of j, and we have yi, y of j. Then what do we have next? And we got a dot product between these pairs. Yep, that's perfect. So this is the finalized vector optimized algorithm which we're going to be using for finding the vector support machine optimizations. So finally, we would be having alpha dot product of u bar plus b greater than or equal to 0. This is from the starting of the lecture. So now let's see how it actually optimizes. So what we would have is we can say a new k function of xi of I, x comma j, and we can say that is equal to let's say a function of 5 of x comma I into the dot product of phi into x of j bar. So you can see how this is going to be the optimization final parameter, since it'll cover all the cases. And this depends on two different formulas which we're going to be using. The first one is going to be u bar into v bar plus 1 whole to the power of n. We have another one called e power minus is equal to x power I minus x power j, the magnitude. We can say that by sigma. So these two are two case conditions for this. That's it, guys. So that's all it to support sector machines.
Hey guys, I hope you learned something out of this video. If you like the videos and if you want to watch more, want to learn about a specific topic, leave it in the comments below. If not, just give it a likes up and subscribe.